All right, so for the next set of slides, we're going to talk about Bayesian reinforcement learning. Now, this particular topic is actually really exciting, and what is interesting and perhaps even a pity is that none of the textbooks cover it. Okay, so here, what I would recommend as a reading is Michael O. Gordon Duff's PhD thesis. So this dates from 2002. It's a beautiful thesis. And then it does explain quite well with lots of text, I guess, the important concepts. And in fact, it was after his thesis that then a lot of people, including myself, ended up working on Bayesian reinforcement learning. Okay, so Bayesian reinforcement learning, we're going to see in a moment that the idea is that we could have model-based and model-free, but for this lecture, we're only going to talk about model-based Bayesian reinforcement learning. And then here, being Bayesian essentially means that when we're trying to learn a model, instead of coming up with an estimate that corresponds to a specific model that might be inaccurate, we're going to model our uncertainty about the model, and therefore we're going to have a distribution over the parameters of our model. This will have a lot of benefits. In particular, it's going to mitigate the bias that would arise in model-based techniques whenever you're estimating a model and it's inaccurate. And then it will also help in terms of balancing the exploration-exploitation trade-off. Okay, so concretely, we'll see three algorithms. There's actually a lot more we could talk about, but I mean for one lecture. So we'll talk about value iteration with a belief model. Then we'll talk about Thompson sampling in Bayesian reinforcement learning. So this will be an extension of what we discussed in the context of bandits. And then we'll see another algorithm called PILCO, which is really a model-based Bayesian actor critique technique that had some really good results. In fact, in terms of efficiency for interactions with the environment, it remains one of the best examples of where people have managed to obtain good results. Okay, so as a quick recap, so we've seen so far model-free and model-based techniques. If you recall, model-free technique, what is nice is that you do direct learning from real experience, and it's unbiased because it's the real experience. Now, the drawback is that we're going to need a lot of interactions with the environment because we're not generalizing in any fashion really when we receive those experiences. With a model-based technique, here we're going to learn in an indirect way. We're typically not learning directly from the real experience. Instead, we're learning a model, and then we're going to learn from our model after that. So it's indirect, the learning. But then one possible problem is that the learning might be biased, right? So if our model is inaccurate, right, then the policy we're going to obtain from that, or the value function we're going to update from that, will reflect these inaccuracies, and therefore is going to be biased. Now, if this bias is not too important, then one of the benefits is that we can get away with having fewer interactions with the environment, in other words, less data. Okay, and then we can combine those two, model-based and model-free, into the DINA framework, where we have here our model-free approach that goes straight from environment to estimating policy value function, and then we've got a model-based technique that first goes through a model and then does planning, right? So this was what we talked about. Okay, so with a model-based approach, the main issue, as we discussed already, is that the model might be inaccurate. So especially at the beginning, when you have just a little bit of data, right, then you estimate a model that cannot be accurate. I mean, there's just no way. If you just have a little bit of data, right, you obviously have a model that is inaccurate. And now if you start planning based on this and then updating your policy based on that, well, garbage in, garbage out will apply. So if you have a model that is inaccurate, you're going to get a policy that is inaccurate. And in fact, here, your policy might just overfit to those inaccuracy and become really bad. Okay, so this is a major problem. So what can we do about this? Well, one solution is to say, well, instead of estimating a single model, let's try to represent the uncertainty in our model. Right? So the problem was that there were inaccuracies, and you know, if we have a little bit of data, we know that our model is inaccurate, so why should we commit to a specific model? We should perhaps simply represent the fact that we still have some uncertainty and then plan based on this. Okay, so just to be concrete, let's say that here we're estimating a transition model, and then perhaps this is using a Gaussian process or maybe a neural network. And then so here maybe we have a little bit of data where this could be the space of state action pairs, and then the y-axis could be essentially the next state. Okay? And then perhaps this is a continuous space. So you see we have for our transition model, we feed in a continuous state action pair, and then it produces on the y-axis as an output the next state. Okay? And then maybe we have a little bit of data, so we've got 6 points here, and then we're starting to estimate our model. But now if we only have 6 points, obviously there's no way the model can be accurate. So here, in terms of models, right, so a model would essentially be a curve that goes through those points. And here I drew 3 curves that all go through those points. Now, which curve should we pick? Right? So it's unclear which curve we should pick, and whatever curve we pick, we can bet that it's going to be an inaccurate curve, right? Like the odds that we're just going to pick the right curve are so low, right, that we're almost certain that our model is inaccurate. Okay, so an alternative, right, so instead of picking a curve here, why don't we represent our uncertainty? So here I've got a graph. This is, in fact, this corresponds to a Gaussian process. So what it does is that instead of committing to a single curve, it has a distribution over curves. And the idea is that here the regions that we can see that are shaded would correspond to plus or minus 1 standard deviation on each side of wherever the curve might be. Okay, so here we're estimating that, okay, there's going to be a curve that connects this point with this one. It will travel somewhere in between, right? And then if I have plus minus 1 standard deviation, this would mean that there's a high probability that wherever the curve is, right, it's going to travel from this point to this point via this region that is shaded. Okay? So this would be something that is much more informative because it tells us that, you see, when I'm going to do planning, I should not assume that my curve, for instance, goes from, I guess, let's say follows the green path, right? Like the green path might be wrong. Maybe it's the red one that's accurate, right? And then so this would be quite far from the red one. So here you see I don't want to commit to a specific curve. And then so here I essentially represent the fact that I think that my curve is somewhere in this region. And then in this particular plot, it would be plus or minus 1 standard deviation. So it means with high confidence, right, or high probability, I would think that my curve is in this region. Now, in fact, when we're Bayesian, what we're going to do is not so much just work with a region. We're going to model a distribution. Right? We're going to say that there's a distribution over where those curves are, and that's what a Gaussian process is going to give us. Okay? So in any case, this picture should help you understand this idea that we're going to model uncertainty, that we're not picking a single model. We're going to have a distribution over the possible models. Okay, so if we do this, Bayesian reinforcement learning, the idea is that we're going to explicitly represent this uncertainty with a distribution, and then the benefits are going to be that now we'll have a better way of balancing the exploration trade-off, because at some level, the reason why we need to explore is whenever in our model there's some region that we're uncertain, so we need to try more often to see what would happen. But then there might be some other regions that we visited quite a bit, and then we are certain or almost certain on what will happen, so we don't need to try these regions again, right? So here, if we model the uncertainty explicitly for this exploration-exploitation trade-off, it now gives us more information so that we can do more targeted or more intelligent exploration. So that's one of the benefits. Okay, and then in a model-based technique, it will help us as well mitigate the model bias. So here again is this idea that with finite amount of data, we know our model is going to be inaccurate. And then instead of just assuming that the model is accurate and then planning based on that, right, let's take into account these inaccuracies, or at least the uncertainty that we have. So then, yeah, this will mitigate the problem of model bias, and then together, overall, it will help us reduce the amount of data that's needed. Now, obviously, these are nice benefits, but there's an obvious drawback, which is going to be that now this is going to get even more complex than anything that we've seen so far. Okay, so in terms of techniques, right, this is going to be complex to implement, and also in terms of the amount of computation, it might take a long time. Okay, so now to get into the details of Bayesian reinforcement learning, let's first recap how we formally defined reinforcement learning. So reinforcement learning, we said that there's some states, some actions, and some rewards. And then we have a model that is unknown. And here I'm going to collapse together the transition and the reward model into a single model that I'm denoting by the property of R and S prime together, given S and A. Right? So the problem of reinforcement learning is essentially this problem where we don't know our model, right? And then we need to find a policy pi, or otherwise a value function q that would map states to actions, or in this case, state-action pairs to cumulative rewards. Right? So that's how we define this. And then the key has been now how to get around the fact that we don't have the model. And here I'm assuming that the model is parameterized by theta, so it really means that I don't know what theta is. Okay, now in Bayesian reinforcement learning, we're going to model the uncertainty. And the way to do this, the idea is that we're going to augment our notion of state with a distribution about the unknown parameters. Right, so if I just go back, the unknown parameters are theta. Okay, so now I'm going to express a distribution with respect to theta, so that now my states are going to have two things. They're going to have the physical states S, as well as some belief states B, where a belief state is really going to be a distribution with respect to theta. So if I'm certain about my model, because I have lots of data and so on, then I'll have a distribution here that is going to be fairly peaked. But if I'm uncertain because I'm just starting and I haven't observed much, then I'm going to have here a distribution that is quite wide. Okay? So the idea is that we augment physical states with belief states, and then together this is known as the information state. And then we're going to condition now the choice of actions based on both the physical and the belief states. Right? So we can now take into account this uncertainty when we select actions. Okay, so now in Bayesian reinforcement learning, everywhere where we had a state, a physical state, now we're going to have as well a belief state, and then together that forms information states, and we're going to work with information states everywhere. So in particular, when we look at the model, now you see the model used to be just the property of R and S prime given S and A, but now we need to augment S with the belief state. So we're going to have property of R, S prime, B prime given S and B as well as A. And now there's something actually very interesting that happens. Once we do this, we can actually show, and we'll see this in a few slides, that the model becomes known. This is very counterintuitive because, I mean, we're in a reinforcement learning setting, right? The model is clearly unknown. We don't know what theta is. And now here I'm claiming that the model becomes known. Okay, so we're going to see in a moment how that's possible. But mathematically it all works out. And then we'll see that this has several advantages because we'll be able to do planning using variable iteration, policy iteration, and so on without resorting necessarily to other techniques that are meant for unknown models. Okay, so in any case, this is the problem of Bayesian reinforcement learning. So we're going to have these different components, including a model that now depends on both S and B. And then so we're going to have this distribution. And I would like to find a policy pi that takes into account both physical and belief states, or otherwise a value function that also maps both physical and belief states with actions to cumulative rewards. Okay? So that's the formal definition. Okay, any questions so far? Okay, very good. All right, so now let's look into more details about this model because I claim that this model is known. So this model is this conditional distribution. I can factor it into something related to the physical model and another part related to the belief model. Right? So here I have R, S prime, B prime. So I'm trying to, so in this model I'm going to predict or have a distribution over the next state, next belief, as well as the reward. Now, the physical part is with respect to R and S. So here I can break this, have a conditional distribution just for R and S. And then I can, using the chain rule, I can express also a conditional distribution with respect to the belief that's going to be conditioned on R and S prime. Right? So here this equation just follows from the chain rule. And there's nothing special really about this other than the interpretation that now we're separating our model into a physical part and a belief part. Okay, so if the overall model is known, then it means that I should also know what is the physical model and what is the belief part. And then we can look at these into more details. So if we start with a physical model, this here can be rewritten as the integral of our unknown model times our belief, where we integrate out the unknown parameters theta. So this is where the justification comes for why this model becomes known, because if it is unknown, so before, when I said that it is unknown, is because I don't know what theta is. And here, when I said that it is known, it's because I don't have theta that appears anywhere. In fact, we're going to integrate it out. So this is what this equation shows here. That if I want to compute a probability over R and S prime at the next time step, right, and I have a belief about theta, so I don't know what theta is, but I have a distribution over theta, what I can do is simply integrate out theta according to my belief, and this will give me an expectation with respect to what R and S prime are going to be. And the reason why taking the expectation here is okay is because overall we're interested in estimating expected rewards, right? So then computing an expectation is just fine. If we had a different objective that had to do with not so much expected rewards, but instead maybe some sort of minimax reward or trying to obtain like the best worst case reward, then there might be some problems with this, okay? But in the context of expected rewards, then this is all right because I'm just taking an expectation, and here the fact that I don't know theta but I have a distribution over theta allows me to integrate out theta, and then at that point I have a distribution that is completely known. Okay, so this is for the physical model. And finally, for the belief model, this distribution can be rewritten in a way where it turns out that we're going to have this probability equal to 1 or 0. It will be 1 when B prime is essentially the posterior of my belief while taking into account S, A, S prime, and R. So you can think of this as the data, right? And now I had originally a belief that represents my uncertainty about the parameters. Now I observe some data, and then I want to take that into account and compute a posterior. So this is here the posterior. We'll see in a few slides how we compute a posterior, but the idea is that B prime is really just the posterior. And then in some of the slides, I'm going to use as a shorthand B with the superscript S, A, S prime, R to indicate that posterior. Okay, so here, if in this expression B prime is indeed the posterior, then the probability will be 1, and if it's not the posterior, it will be 0. So what this really means is that B prime, we don't really have a distribution over it. We know what it's going to be. There's a deterministic transition that happens where we go from our prior to our posterior according to Bayes' theorem. That's really what this means. So here, this is the maze problem that we talked about several lectures ago. Very simple problem. And then in this maze problem, so we are in different cells, possibly. And then let's say that we've got a policy here where we would execute the action up, and then right, and then right, and right, and then end up into this state where we earn a reward of +1. Okay? So this is ideally what should happen, right? So if we do up, up, and then right, 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 then we get +1. Now, the idea is that there's some uncertainty, there's some stochasticity in those actions, and therefore we have a transition model that would normally have some parameter here, theta, that would indicate perhaps the probability that, let's say I go right. Okay, so let's say I'm in cell ij, and then I go right. Now, what's the probability that I would end up in cell I prime j prime? According to what I formulated here, right? So if I prime is I plus 1 and j prime is equal to j, so for instance, if I'm in this cell here, and then I prime would be I plus 1, so it would be this column, and then j would be the same row, so it means that I'm actually moving right. So here this would be the probability, theta, that if I execute the action right, I will end up going right indeed. Okay? But now, this is not necessarily probability 1. It could be a probability less than 1, like maybe 0.9 or 0.8 or 0.7, right? So we're not sure. And then if we don't end up going right, there's a possibility that we're going to end up into a different state where here, let's say that I prime is the same as I, but then j prime is either j plus 1 or j minus 1. So what this would mean is that we're trying to go right, and either we end up going up or we end up going down. Okay? So this is obviously a simple synthetic problem, but in any case, we could then say that the probability of this happening could be 1 minus theta divided by 2. Okay? And then the probability of ending up anywhere else perhaps could be 0. So this sums up to 1. Okay? So here this is a very, very simple problem where there's one parameter theta. Here I gave the example for the action right. I can do the same thing for the action up. So if I end up going up, the probability will be theta. If I go left or right instead, then the probability will be 1 minus theta divided by 2. And then anywhere else, it'll be 0. Okay? And then I can do this for the other actions as well. Okay, so this is a simple example where now what's clear is that our model has one parameter, theta, right? And then what I need to do now is perhaps estimate that. Or at least at the beginning, I don't know what theta is. And then if I'm going to be Bayesian, I'm going to start with some distribution with respect to theta, and then compute a posterior and update this as I go. And any questions regarding this setting so far? Yeah?
The Do you believe that theta is the same in both equations?
Yeah, so here, just to keep the problem really simple, right? So I designed it in a way where there's a single parameter theta for all of the equations, okay? But in practice, you're absolutely right here that we probably do want to consider much more complex domains where there will be multiple parameters, maybe depending on which action or which state we're in, then there would be different parameters, so there would be a whole vector of parameters. Yeah.
Where do we get a model?
So here, this model, yeah, I guess, yeah, I said that here the model is unknown, right? But at some level, what we're doing still is using some prior knowledge where because we know it's a maze problem, we know that the actions up, right, left, down, and so on would correspond to like going to an adjacent cell. And then perhaps we know that it doesn't matter what location we're in, it's really just dependent on the action. And then, so this would be something that could be formulated based on our prior knowledge. I mean, this is obviously something simple, synthetic that I designed just for the sake of an example. But very concretely, let's say that you have a mobile robot, and then your mobile robot, you would like to express a transition model for what happens when you give it a command of going forward by, let's say, 10 centimeters. Well, so here, depending on the surface that it's on, if it's on a hardwood floor versus ceramic versus carpet, right, then the wheels might slip more or less, and then there will be a different transition model based on that. Okay, so then it's common in that case to formulate transition models that would take that into account. Okay, but yeah, in general here, the idea is that you would formulate some model with some parameters, and what is unknown are the parameters, but the structure of the model is something that you would simply elicit from your prior knowledge, from your domain knowledge.
Wait, let's say if you go up, but you actually end up going down, would it still work with this model?
Okay, in this model, it's saying that the probability is 0. Okay, so this should not happen. It's impossible according to this model. Okay, but okay, here, yeah, in general, I guess what you're pointing at is that it's dangerous to have 0 probabilities, right? So in practice, yeah, we try not to have anything that has 0 probabilities, because even if something looks like it's impossible, like, I mean, if I give my robot a command to go forward, I mean, sure, it can slip and maybe go slightly in a different direction, but would it actually go backwards, right? And then, so here, you know, even if this looks like it should not happen, and therefore we could give it a probability 0, it's hard to imagine all possible cases. And in fact, here I can think of my robotic vacuum cleaner at home that I've seen it essentially try to get onto the carpet, and then it might actually slip backwards. And then so anything's possible. So yeah, in practice, we probably want to avoid a 0 probability, because then that could lead to all kinds of problems down the road. Yeah. Any other questions? Yeah.
Isn't that theta has only one solution as well?
Sorry, you're asking if there's only one solution?
Yeah, one solution for theta, because the 3 possibilities is up to 1, so theta has to be 1.
Well, theta is going to be a number between 0 and 1. Okay, and then yeah, here I'm assuming that it will take a single value, therefore there will be a single solution. And then in general, like, there is a true underlying model, right, that has some specific distribution with respect to next states. And then, yeah, in general, we are assuming that there will be a single solution. Yeah. Okay. All right, so now that I've specified this, let's see how we can do, let's see how we can express a belief, right? So theta is our unknown parameter. So here I'm going to express a distribution with respect to theta. And then because theta is a probability, it's a number between 0 and 1, then there is a class of distributions that essentially have support precisely on the 0-1 interval, and that's the class of beta distribution. So the beta distribution is has the following algebraic form. So there's a constant times theta raised to the power of alpha minus 1 times 1 minus theta raised to the power of beta minus 1. Right? And then we saw previously the beta distribution in the context of the coin example. Now here it's a different example where we've got a little maze, but then still the idea is that theta is a parameter, a probability that's between 0 and 1, and then the beta distribution is useful to express a distribution over that range of 0, 1. Okay, so we start with this. Here, I mean, this is a modeling choice as well. Okay, so the beta distribution is not the only one that we might want to choose, right? So there might be, I mean, there's all kinds of other distributions that we could consider, but it's a convenient one. And then using Bayes' theorem, now if I am in state S, then I execute action A, and then I end up in state S prime, I will get a triple, right? And then I can compute a posterior, which will be the probability of theta given SA and S prime. And then the posterior will be proportional to the prior times the likelihood. Okay? So here, again, this is similar to what we've seen in the context of the coin example, but now it's not necessarily, I mean, there's no coin here. It's more about a robot in a maze that will go from one state to another, and then we can update the posterior in this fashion. Okay, so here, yeah, if I take a concrete state, let's say I'm in state ij in the maze, and then I end up, after executing the action up, in state I prime, j prime, then I would want to compute my posterior distribution, which would be the belief of theta given ij up I prime, j prime, and then it will correspond to this update, specifically if I consider I prime that's equal to I and j prime that's equal to j plus 1. So if you recall, I corresponds to the columns and then j corresponds to the rows. So here we're saying that we're staying in the same column, but then we're going up by one row. So that corresponds precisely to the action of going up. So as a result, you see when I multiply my prior by the likelihood of actually going up when I execute the action up, if I just go back in the example, right? So for the action up, if I actually go up, the probability of doing this would be theta. So here I'm going to replace in my equation this likelihood by theta, and then I also replace my prior by the beta distribution. I multiply those two, so theta will be absorbed into this term here. So we're going to simply increase the exponent to be equal to alpha. And now this expression is essentially another beta distribution where we've simply incremented alpha. Okay? Any questions regarding this? Okay, good. So yeah, so this should be similar to what we talked about earlier in the context of the coin example, but now here it's a different example with a maze. Okay. Now if, let's say that I consider my physical model, the physical model, this is the distribution over the physical state S prime given S, B, and A. So we said earlier that the model would actually be known once I go Bayesian, right? And then the key is that for the physical part, I would simply integrate out theta. Okay, so here I've got my unknown model, or at least my model with the unknown parameter theta, but then I've got my belief with respect to theta, and then I can simply integrate out theta to get a prediction about my next state. And then, so it's a matter of computing this integral. So here I can simply take my likelihood again. So this is the probability of going to I prime, j prime, given that I'm in I, j, and let's say for this example that I'm going to use the action right. So here I'm just changing the example, but so it's a different action, the action right. And then again, I have my beta distribution for the prior. Now, this case where I execute the action right, and then I choose, let's say, I prime to be equal to I and j prime to be equal to j minus 1. So here this means that the column stays the same, so I is the same, right? And then for the row, we're going down by one row. So it's effectively, we've just executed the action right, but then because of this, we are in fact going down. Okay, so then the probability of this happening is going to be 1 minus theta divided by 2, right? Because that's what we discussed in the model here. So if I execute the action right, and then j prime is equal to j minus 1, right? Then we're in this case here with 1 minus theta divided by 2. So that's what I'm going to plug in right here. Okay, so right here. So now I can multiply that together and then integrate out theta. Here I'm skipping a lot of steps, but basically this integral has a nice solution, and it turns out to be equal to beta divided by 2. Okay. Actually, wait a second. No, is it beta divided by 2? No, that's not right. So it should be beta divided by 2 times alpha plus beta. Yes. Okay, so let me write this down here. So yeah, there's a typo here. So this should be simply beta divided by 2 times alpha plus beta. Okay. So the idea is that this can be thought as we're taking the beta distribution times an expression. And this expression, you can think of it as like now computing an expectation. So I'm computing whatever is the mean of this beta distribution. And then the division by 2 will carry through. So that's why we've got this division by 2. And now this expectation with respect to 1 minus theta happens to be beta divided by alpha plus beta. Okay? So that's why I've got here beta divided by alpha plus beta. Okay. Any questions regarding this? Okay. Good. All right. So what I've just shown you is you see that I can come up with a predictive distribution with respect to the physical model, and before that, we also saw how we can update our belief. So it means that in here, now I've just given you an example for both the belief model and the physical model, how I can obtain them in the context of this particular maze problem. Now in practice, obviously there's going to be more parameters, but it's the same idea. Okay, so as long as you can compute these things, so here compute this integral, and here compute the posterior distribution, then you're in good shape. So you can work with the full model. So you're going to have a distribution here. Okay, so once we've got this, then what we can do is planning. So now you see when I introduced Bayesian reinforcement learning, in this case here it was model-based Bayesian reinforcement learning, right? Then the model becomes known. So here we could actually use planning techniques. We can use value iteration, we can use policy iteration, we can use all kinds of other techniques for planning. And then effectively, Bayesian reinforcement learning would correspond to a Markov decision process. Okay, it's a Markov decision process, although it's a complex Markov decision process, because now the states are really the physical states with the belief states together that form the information state. So we have to do the planning with respect to the information states. Okay, the benefit of this is that now, yeah, we can solve the planning problem using classic techniques. Although the classic techniques are going to have to use function approximators because the information state includes the belief, which is itself a distribution. Therefore, it's something complex to represent. But still, as long as we can do this, one of the nice benefits is that then we will naturally optimize the exploration-exploitation trade-off. In fact, here we can show that we're going to do this trade-off in an optimal way with respect to the prior distribution. Okay, so the prior distribution, so our initial belief, right, then might incorporate some information. And with respect to that, you can show that Bayesian reinforcement learning, where you solve the planning problem, will end up balancing exploration and exploitation in an optimal way. Now, how do we see this? The key is to look at Bellman's equation. So in this case, you see, for Bayesian reinforcement learning, we said that we're always going to augment the state with a notion of belief to get an information state. So now I can rewrite Bellman's equation where everywhere I had an S, I'm going to augment that with a B for a belief. So now my rewards are going to depend on this. And then I will also have a distribution over the next state that depends on the belief. And then here my value function going forward in time will also depend on the belief. Okay? So this is Bellman's equation that's now been adjusted to include beliefs. Okay, so, and then in this equation, you might ask, how do I get this expectation of the rewards? So here, let's say that, because I talked a lot about the transition model that we're learning, but then we can also do the same thing with respect to the reward model. So how do we get this expectation? So this expectation, there's also an integral where normally the expectation should be simply the probability density function with respect to R times R, and then we integrate R. But then that depends on theta, and then we have our belief with respect to theta, so we also integrate theta. Okay? So to get this expectation, right, then we need to do those two steps of integration. The first step is just the regular steps where we always just sum out or integrate out the rewards, but then the second step is where we also integrate out theta. Okay? So now at that point, you see, in the equation, we have a reward, an expected reward that is known based on this equation. And then here, this is our predictive distribution with respect to the physical state that depends on B instead of theta and therefore is known. So that's how we can use that for planning. Okay, any questions? Yes?
So the simple example you introduced earlier where the single parameter theta parameterized the whole transition distribution, that would not be sufficient even to cover like the distribution of the reward, right? Would you have to have some separate model completely in addition to that, because you can't assume, like even if you know the transition probabilities, you still can't assume you know what the reward would be based on which state you transition to?
Right, yeah, so that's a great question. So here, yeah, the example I gave, I actually assumed that we knew the reward model already. Okay, so here I wanted to make it very simple. So I just said what we're going to treat as unknown is a transition model, but then for the reward, let's just assume that it's minus 0.04 for all non-terminal states, and then minus 1 and plus 1 for those two states. But now what if we don't know the reward model as well, right? So that's going to require some parameters. And here in the slides, what I'm doing is I'm using theta to essentially capture the parameters of both the transition and the reward model. But presumably, some of those parameters would be specific to the reward, and some other parameters would be specific to the transition. And then, so the integrals we would carry out might be different as a result. Yeah. Okay. Yes?
So instead of doing these integrals, I guess we can as well do a Monte Carlo approximation if it's too hard to.
Absolutely, yes. So in practice, whenever we cannot perform those integrals exactly, or at least in closed form, then we would approximate via Monte Carlo estimate. So just sample and take an average of the samples. So yeah, so you can always approximate that. So I guess, yeah, here I'm showing the exact equations. And this is sort of like mathematically what you're trying to do. Now, algorithmically, right, then these equations might not be something computable. So then you might need to do some approximations for each one of those integrals. And then integrals in general, the key is that we can approximate them by sampling, right? So these are really expectations, so you can always sample. Well, actually, it's often easier to sample. I shouldn't say that you can always sample because, yeah, some distributions are actually hard to sample from as well, okay? But in any case, you can often get away by sampling. Yeah. Okay, and now, yeah, let's continue. So, okay, concretely, if let's say we wanted to do value iteration, then what we would do is simply take Bellman's equation, turn it into an update where, okay, initially we start by computing the value when there's no time steps left. So V0 is when there's no time step left. And then so this would be just the immediate reward that, and here we would compute the expectation and then select the action that maximizes that, okay? Now, for all the other time steps, so when there's 1 to h time steps left to go into the planning, then we would essentially perform a Bellman backup. And yeah, that's a mathematical equation that we would compute. But then, as we just discussed, here, this equation might not be something computable, and then you might want to represent the value function by some function approximator. So it could be a linear function approximator, could be a neural network, and so on. And then even to get the predictive distribution as well as the reward, then you might need to do some approximation. So, okay, so this is traditional value iteration. In fact, what you coded for assignment 1 is right here. But now, how do we do this in the context of Bayesian reinforcement learning, where we have a Markov decision process that has information states, right? Then it's essentially the equation on the previous slide, where now I augment all the states that I see everywhere with some belief. Okay, so that's how you see I've got a belief in the value function, into the transition model, into the reward, the expected reward, and so on. But it's essentially the same thing. Okay? So now, if you're already working here with a function approximator, right, where you normally approximate your value function by a neural network that takes as input your state description and then produces as output a value, then here this won't be much harder because you can now have as input to your value function your physical state descriptor as well as a descriptor for the belief state. Okay? So you just feed that into the neural network, and then what you want is a value to come as output. So you just have, a longer vector that you feed into the neural network. But otherwise, everything would work in the same way. Yeah?
What's the dimension of B?
What's the dimension of B? Okay, so that depends on the problem. That depends on how you formulate your belief. Okay, so if I just go back for the maze problem, for instance, here you see theta is really just one number between 0 and 1. And now we express a beta distribution with respect to theta. So the beta distribution has two hyperparameters, alpha and beta. So in this case, B would essentially be a vector of two values that corresponds to alpha and beta. So it depends on what distribution we use. In some other contexts, you might want to use a Gaussian distribution. And then if it's a Gaussian distribution, let's say, with respect to just a scalar, then again, you would have a mean and a variance, so 2 parameters. But if it's a Gaussian distribution with respect to a vector of n dimensions, then you would have a vector as well of n dimensions for the mean, and then a covariance matrix that would be n squared, right? So then it would be a much larger vector. And this is just for a Gaussian. Now, and this is just with respect to like, something simple, but in practice, you might want to use like fairly complex distributions, but then you have to look at what are the parameters of those distributions, and that's what would determine the representation of B. Yeah?
The belief be updated as well in the value iteration because you are doing Bayesian learning, right?
Yes, okay, good point. So, yes, so the belief is indeed updated in value iteration. So yeah, let's go here. So if you look here, what I wrote is B superscript S A S prime, right? That corresponds to the posterior belief after we've observed S A and S prime, right? And this posterior belief is obtained here, right? So this is B S A S prime, right? So, and that's the posterior belief that comes from multiplying my original belief times the likelihood and then normalizing. Okay? Yeah, exactly. So here there's an update step that I need to make. And in comparison, you see, when we do value iteration with a regular MDP, we just have S prime, right? So there's nothing to be computed to get S prime. The environment gives us S prime. Now here, the environment also gives me S prime, but then for B S A S prime, the environment doesn't give me that. This is a belief, right? So it's some belief that I have, and I need to update it. I need to figure it out for myself, right? So then that corresponds to the posterior distribution, and so I need to compute that, and that too might need to be approximated. Yeah. Okay, so let's come back to the exploration-exploitation trade-off, right? So traditionally in reinforcement learning, there's a dilemma, and then you typically ask the following question: should I maximize my immediate rewards, which would correspond to exploitation, or should I maximize my information gain, which corresponds to exploration? And here, once we are in the Bayesian setting, we can actually argue that this is not the right question, okay? At the end of the day, everything just boils down to maximizing rewards. So we really just have a single objective. We're going to maximize the expected total rewards. And then here, the idea is that now the rewards are not depending just on the physical state, but are also dependent on my belief, so the information state. Okay, so you see, when I formulated Bayesian reinforcement learning, I showed that it's equivalent to a belief state MDP, okay, or sorry, an information state MDP, in which everything is known, and then because everything is known and it's a regular MDP, it just happens to have a state that has two parts, the physical state and the belief, right? Then, but still, it's an MDP. Well, for that MDP, we know from the theory of MDPs that I can compute an optimal value function by value iteration, and then that optimal value function will be greater than any other value function, and then this value function is really the sum of the rewards. So basically, you see, if I solve this MDP, I am finding a policy that will give me the best way of maximizing my rewards. And here you could say, well, when I execute this policy, what if there's a better way of doing exploration? Well, if you choose the actions differently than what this policy suggests, then you will actually be executing a suboptimal policy with respect to what we know of a Markov decision process. And then as a result, if it's suboptimal, you're going to earn less rewards. And then this alternative way of exploring is not going to be optimal, right? So the optimal way of exploring is in fact to follow the Bayesian approach to select actions in a way that will maximize the sum of the rewards. We really just have one objective, and then again, because we formulated this as an MDP, we know from the theory of MDPs that there's going to be an optimal value function. We know we can obtain it by value iteration or some of these other algorithms, and then any other policy would necessarily have a value function that is lower. So if you're doing something else in terms of exploration, and then you earn less rewards, that can't be as good, right? So that's why this will be suboptimal. So in any case, then what this all means is that we can solve in a principled way and then in an optimal way this exploration-exploitation trade-off by Bayesian reinforcement learning. And here, perhaps, the thing I should highlight is that it is optimal, but with respect to whatever prior knowledge we start with in our prior distribution. Okay, so the initial belief that we start with will include some prior information because it's a specific distribution, right? And then it will be optimal with respect to that. But now if someone else starts with a different distribution, or if the environment actually behaves differently than this initial distribution, it might not be optimal. But otherwise, that's the only thing here that might make it non-optimal, right? So it's the prior distribution and then a prior knowledge that's embedded in there. Any questions regarding this? Okay. Good. So, all right. So now let's say that we want to go ahead and do some Bayesian reinforcement learning. Here, what is typical will be to have two phases. An offline phase where we're going to do planning, and then an online phase where we're going to do execution. So in everything we've done so far in reinforcement learning, there was no such thing as an offline or an online phase. You would essentially throw your agent into the environment, and then it would start acting, and then it would collect rewards as it goes, and then it would learn as it goes, and then it would refine its policy as it goes. But now here, what's really interesting is that it's like saying that before I throw myself into the environment, it's like saying, let me think for a little while, let me plan carefully what I'm going to do once I'm in the environment. Okay, so this offline planning phase, right, you're essentially figuring out what you're going to do, how you're going to select your actions. So you're coming up with a very general policy that will be optimal with respect to exploration. You're essentially figuring out how you're going to do the exploration. And then once the online execution starts, then you get into the environment, you start executing the actions, and then at that point, you're essentially just following the policy that was determined here. But this policy is essentially the policy that was obtained to do this exploration in an optimal way. Okay, so yeah, so then the planning part, we're finding a policy pi, or otherwise a value function v star, from which we can derive a policy. We can solve that by policy or value iteration, or any other algorithm that we've discussed. And then once you have that, then you go to the environment and you start executing the policy. So you start in some physical state as 0. You also start with some initial belief B0. And then at every step, you execute the policy. So you select an action according to your policy that you optimized here. This policy takes as input both the physical state and the belief, right? So then it will be able to balance the exploration exploitation trade-off because of that. And then so it chooses the action. Then you receive the next state and then the reward. Then based on this, now you update the belief. So the belief now, we compute the posterior distribution. So it will depend on the next state, action, reward. So actually, current state, action, reward, and then next state. So we're going to compute this posterior belief and then repeat. Okay, so after this, then we simply execute the action and so on. So it's a very different mode because here in principle we can plan ahead, although to be fair, this planning, because it's planning to come up with what would be the best exploration strategy, and this is with respect to any possible environment, it's going to be a very difficult policy to obtain. But in theory, if you get that optimal policy, then you have an optimal way of exploring, and then at that point, once you're thrown into the environment, then all you have to do is execute this policy, and then there's no explicit learning per se. All you have to do is really just update your belief. So the learning that you're really doing is just learning with respect to the unknown parameter theta. Right? So normally in all the other parts of, all the other types of reinforcement learning that we discussed, what happens is that you're learning about the policy, or you're learning about the Q function as you go. Now here, what we're learning as we go is simply we're trying to refine our belief about the unknown parameter theta for our model. Because whatever is our belief, we've already planned here what we're going to do. Okay, and so all we're missing is to know what is our current belief, and then this, in the long run, will essentially converge towards the true parameter theta as long as we have a belief update that is implemented accurately and that we have a distribution that has the right support. Okay? Yeah?
So in how far is this related to active learning? So will this basically perform the action that will extract most information about the world in order to update the belief?
Yes, yes, exactly. So yeah, so here it will execute the action that will extract information, not necessarily the most information, but it will extract the right amount of information so that you can get a lot of immediate reward and a lot of future rewards. Because what you care about is the sum of all rewards, immediate and future. And normally the exploration-exploitation trade-off is this trade-off where you're not sure whether you should select an action that gives you a high reward right now or select an action that will allow you to learn something so that you can earn high rewards in the future. But I mean, these things are added together into the objective, right? So we're trying to maximize sum of rewards. So that's why here this action does both, right? It's been chosen to essentially just maximize that sum, so it will do the right thing in terms of trading, exploration, and exploitation. Yeah?
In this offline planning phase, we're finding the policy or the value iteration for an arbitrary belief at some, not a belief that we have at this point in time, right? So it's over potentially any belief, or is it over the belief that we have right now?
Okay, yeah, in the offline planning phase, then we don't know what beliefs we're going to be in at any point in time. So here, at least the way I formulated this, we would have to plan with respect to all possible beliefs, and that's why this is going to be something really complex. So the reality is that in practice, this is very difficult to achieve, and then we always end up approximating. And then, yeah, I would say it's not practical to find necessarily this pi star or v star. Okay, yeah, I think we're going to see in a moment in the next few slides some approach to essentially do some partial planning that will take into account what is our current belief as opposed to try to plan for all beliefs. This is yeah, if we just want to do like what is the simplest thing conceptually, but not necessarily the simplest computationally, right, then we would just do this planning for everything. But you're absolutely right that in practice what we want to do is take into account our current belief, do some planning with respect to that, and that might alleviate a lot of the concerns. Yeah.
Consider we have already had the pi star and v star. It's optimized over all the beliefs, right? But why do we use it in the second phase? Like, so here the pi is for special belief,
So pi is a mapping from S and B to an action. And then so it takes as input a state and a belief, right? And then it returns an action. So here, yeah, we need to optimize this so that it's going to give us the best action, whatever belief we end up in. And then when we get to the execution phase here, then we simply update our belief, and then we plug that into our policy to get the action.
I guess the question was, since in the first iteration, pi star will only, we only need to compute pi star for b equals our initial state. So it should also be possible to just update the belief and then compute the pi star for the belief that we obtain then.
Yes, okay, yes. So here, if we do this offline planning phase, pi star should be good for all beliefs, but what you're pointing out is that, okay, maybe we don't do this offline planning phase, and what we could do is simply start executing here, look at what is B0, and then do planning with respect to B0 just to get that first action, right? And that'll be a much simpler planning problem. Yeah, and then we update our belief. We're going to get the next belief, the posterior here, and then again we could do planning and then obtain the next, the next action and so on. Yeah, so I believe this is what I have on the next slides. Yeah, so here, exactly. So here, offline planning is notoriously difficult. This is for several reasons. One of them is that we have to use some function approximators for the model. This could include Gaussian processes or neural networks. So we're going to use that for the model, for the value function, for the policy. So for essentially every part that we considered, right, we're typically going to use a function approximator. And then here, our notion of state, because it includes the belief, where the belief is a distribution that is parameterized by some hyperparameters, and then these are typically going to be continuous, then our state space includes the belief space, which is continuous, and therefore it's going to make the planning difficult. Like we're not going to be able to use, for instance, tabular value iteration or policy iteration. Okay, so that's why we really have to use a function approximator. Now these are issues, these are challenges, but they can be addressed through function approximators. What is more problematic is what I highlighted here, which is that a good plan essentially would implicitly account for all possible environments, and this will be intractable. So is this notion that I guess we are planning for all possible beliefs. Those beliefs are with respect to all possible environments, right? And then so it will generally be intractable to do this. Okay, so the alternative will be to do online partial planning. So instead of having an offline phase where we do all of our planning, right, what we could do is simply wait and see what belief we end up in at every step, and then do partial planning from that point on. And here, let me mention briefly two approaches. In fact, there's many approaches. These are just two examples. So Thompson sampling. So this will be similar to what we've seen in the context of bandits. And also another algorithm called PILCO that does model-based, it's a model-based Bayesian actor critique. Okay, so Thompson sampling. If you recall the idea, I mean, we've seen this algorithm in the context of bandits, but it is also very useful in the context of full Bayesian reinforcement learning, where we have multiple states. The idea is that at any point in time, we're going to sample some model theta I, and then plan for that particular model, so that particular MDP. Okay, so normally we have a belief with respect to theta. Theta is unknown, so we have a belief with respect to that. And instead of working with beliefs, which are distributions which are complex and so on, what we can do is simply sample one theta, so one model that corresponds to an MDP, and then plan with respect to that. Because we know how to plan with respect to a regular MDP where the model is specified, so this will be much simpler. Okay, so concretely, Thompson sampling would work as follows. So we start with our belief, which is a distribution over theta, and now we're going to sample a bunch of parameters, so a bunch of models, theta 1 up through theta k. Then for each one of them, we're going to solve the MDP, because theta I defines a specific MDP, so we're going to solve that. And let's say in this case, when we solve it, it gives us a Q function. Okay, so we could use value iteration to give us a Q function, or we could use Q learning, so we can use all kinds of algorithms to solve this, and then get a Q function. Now, once we have that, then because we took K samples, what we could do is simply take the average of the Q functions to get an estimate. So this would be an estimate of what the Q function would be if I was working really with the distribution probability of theta here. Okay? So, and now based on that, I can simply select the action that would maximize this Q value, execute it, receive the next reward and state, and then update my belief. So if you recall with Thompson sampling, what happens is that at any point in time, we have a distribution with respect to whatever is unknown. When we discussed this in the context of bandits, it was the rewards that were unknown. Here, it's not just the rewards, but also the transition model. So I'm capturing all of this through theta. So theta are the parameters that capture everything that is unknown. So I have a distribution with respect to that, and I'm just going to sample a few thetas, find out what is the optimal thing to do, or at least the optimal Q function with respect to each one of them. And now I'm going to take the average, because I mean here these were just samples, so I'm just going to take the average, and then after that select the action that would maximize this average, right? So this will not necessarily do optimal exploration exploitation, because here we're not selecting actions necessarily by having solved the full information state MDP, but it will give us a way of doing exploration that will take into account what we don't know and is expressed through this distribution. Okay? Yeah?
It is really good idea to average Q functions because, for example, in these simple grid worlds, even a small change in a parameter may result in the optimal policy that you might that should be executed to be completely different. So, for example, there's the policy of moving to the left, first to the left, or to the right and then down, or first moving down and then to the left.
Right. Okay. So here taking the average with respect to those Q function really comes from the fact that here I sample theta. Okay. And then we discussed earlier. If I just go back a few slides. Let's see. I want this equation. Yeah. So like for instance, you see. Here, to compute my expected reward, I have to do an integral with respect to theta. And then for my transition model with respect to B, I also have to do an integral with respect to theta. Those integrals might be difficult to do, right? And then we discuss how we might want to just approximate that through sampling. So here, now instead of just approximating the predictive distribution and then approximating just the expected reward, why don't I approximate the computation of the entire thing? And now the entire thing here depends on really the belief. So there is an embedded expectation with respect to theta throughout the entire equation. And now, so if I just sample one theta, solve the Bellman equation with respect to that theta, and then do the same thing for the next theta and so on, and then take the average, it will end up being an approximation to this. Okay? So that's really what's going on here. So yeah, so that's why it's okay to do this. Yeah. Yes?
In your first line, you have for all A. Is that a typo held over from posterior bandits?
Yes, yeah, that's a typo. So yeah, so this should not be here. Oh, no, wait a second. So I need to do something for all A at some point, so I guess, oh no, I do have the argmax with respect to A here. So I guess, yeah, this is just a typo, so I should remove this. There's no for all A, because yeah, here we would, it doesn't depend on the actions per se, right? So we would simply sample some model. Yeah, good. Okay. All right, let's see a second approach. This one is a model-based Bayesian actor critique. It's a very interesting approach proposed in 2011 by these authors, so Desenroth and Rasmussen. And then this was before the deep revolution, the deep neural network revolution. So they used Gaussian processes to model their transition model. And then there was a follow-up paper in 2016 called Deep Pilco. So essentially they replaced the Gaussian process by a Bayesian neural network. Okay, so the algorithm works as follows. So you have two loops. The inner loop here, there's this actor critique. So the critique is essentially computing the value of a policy. Okay, so it's going to evaluate a policy. So here I've got a policy pi that's going to be represented, let's say, by a neural network or any type of function approximator. I've got my belief, which is here a distribution over models. And then, so I'm going to simply evaluate that policy. So this gives me a value function. And then the actor now is going to take a step in the direction of the gradient, where we essentially look at the gradient of the value function with respect to the policy. Okay, so yeah, so it's a gradient update to the policy, and then we simply iterate between those two. So you see this is similar to doing like policy evaluation and then policy improvement as in policy iteration, but now because we're in a continuous space, the policy improvement has to be done based on gradients as opposed to a temporal difference update. Okay, so yeah, so then we take a step in the direction of a gradient. So we simply repeat this, and this is all based on a specific belief. Okay, and then the outer loop after that will execute whatever action was decided by the policy for the current state and belief, and then it will update the belief. It will compute a posterior belief. Okay, so you see this is a case where now there's no offline planning phase. It's all online, right? So at every step, we execute an action, and then after that, when we execute that action, that allows us to learn something to update our belief about the environment, about the model. So we compute an updated belief. But once we have an updated belief, now we have to redo the planning, right? So this inner loop here with the critique is essentially evaluating how good is that policy with respect to that belief, then updating it by doing a gradient update, and then going back and forth between those two until we've converged to what appears to be a good policy for that belief, right? So now we don't have a model, but instead we have a belief, okay? So yeah, so this is very similar to actor critiques that we've seen before, but the actor critiques that we discussed before, the idea is that we, we might have had a model or not, and then the key is that we were simply computing a value function. So we are doing that here too, but then we are exploiting the fact that we have a model so that we can do this type of update. Okay, so this approach was very interesting because in practice, it achieved unprecedented data efficiency. Okay, so reinforcement learning, I mean, by now you guys have done assignment 1, so you played with the cart pole problem, right? And then for the cart pole problem, you had to train it for thousands of episodes, right, before it might converge. And then it depends on whether you use a replay buffer in the case of DQN, and then There's all kinds of aspects to the algorithm that will impact how long it will take, right? But then it's still not exploring in a good way. So here, by using a Bayesian approach, the idea is that when you think about the cart pole, right, like forget about this class, just think, in the simplest way. Let's say I give you a stick and I ask you to balance it, right? This is essentially the cart pole problem. As a human, you can learn to balance a stick fairly quickly. Okay, you might have to practice a little bit, but I mean, if the stick is in fact long enough, you'll be able to balance it, and you don't have to take thousands of episodes to do this, right? And then the model really for the stick is that there is gravity that pulls it down on one side or the other, and I mean, the dynamics of the environment are simple, right? So it shouldn't take that long to learn to balance a stick if we are able to learn a good model of the environment, given that the environment is simple. So here, what this shows is, for instance, for the cart pole problem, some other algorithms before this work, they needed a certain amount of time for interacting with the environment. So here they were actually using a physical cart pole, so it was not a simulated cart pole like you did in assignment 1, so it was a physical one, but then this was the amount of time in second, and then you can see that I mean, most of the other approaches were already taking at least 100 seconds. Some of them were like around 100,000 seconds, so it was quite long. Okay, and in Pilco, just takes a few seconds. Okay, so it's very fast. Now it's not just on cart pole. So there's in fact a more complicated cart with a double pole. Okay, so it has a hinge between two poles. And then there's another problem, another toy problem about learning to ride a bicycle, in fact a unicycle. And then so you've got a sense here of how many trials and then how much time it needs to train with the environment before it manages to find a good policy. Okay, so this was, it showed that you can explore very effectively and then start exploiting when is the right time and then obtain a good policy very quickly.